Hey there, students, and welcome to today's Explainer. I am absolutely stoked to be guiding you through this masterclass on CNC lathe programming using Mastercam. Whether you're just dipping your toes into computer-aided manufacturing, or you're already chip making and just want to sharpen those digital skills, you're exactly where you need to be. Today, we're taking a journey from a totally blank digital canvas straight through to a machine-ready turning operation. We're going to dig into the interface, plot out our geometry, and lock down the exact parameters we need to tell our lathe exactly how to cut metal. So grab your digital calipers and let's get right into it.
So, here's our roadmap for this session. First, we'll tackle the initial setup. Then, we'll move on to creating our 2D drawing. After that, it's time for roughing and finishing operations. And finally, we'll wrap things up with post-processing. Let's get started.
All right, part 1, initial Mastercam setup. Before we even think about drawing a single line, we have to give our software the right brain for the job. Up in the top ribbon, you're going to click the Machine menu, hit the Lathe dropdown, and just select Default. It's pretty straightforward, but it's absolutely crucial. This tells Mastercam, hey, load the turning properties instead of, say, milling or wire EDM. The moment you do that, you'll see Machine Group 1 instantly pop up in your Toolpath Manager right there on the side of your screen.
Now pay attention here, because this specific step trips up a lot of beginners. When you look at the Planes Manager, you're going to see the usual suspects like top, front, and right. But we're programming a lathe, right? So we need a very specific orientation. You'll actually spot two newly generated planes, lathe Z equals world Z and plus D plus Z. You absolutely must select that plus D plus Z plane and click the equals button at the top to make it your active plane. Why? Well, think about a physical lathe. The cross slide moves in the x-axis to control your part's diameter. By picking the plus D plus Z plane, we're basically telling Mastercam that our vertical drawing axis, the D+, represents the diameter, which is that physical x-axis on the machine. Trust me, setting this up now makes plotting your coordinates way more intuitive later.
Okay, moving right along to part 2, creating 2D drawings.
Let's take a good look at our target blueprint. As you can see, we're working with a stepped shaft. Our total overall length is 100 millimeters. Now, the largest diameter is 50 millimeters, and then it steps down to a 48 millimeter diameter, holding that for a length of 50 millimeters. I want you to lock these three numbers into your brain, students: 100, 50, and 48. These are the exact dimensions we're going to be feeding into the software in just a second.
So to actually build out that geometry, we're going to head over to the wireframe menu and grab the Line Endpoints command. Now, a quick rule of thumb. Everything we draw for a lathe profile starts right from the origin point. That's coordinate 0, 0. And practically speaking, that 0 point represents the absolute front center face of your raw, unmachined stock. From that exact origin, we're going to start plotting our lines outward to trace out just the top half of our part's profile.
Let's see how this actually builds out in real time. Mastercam is incredibly fast for drafting if, and this is a big if, you use your keyboard efficiently. Once you click your 0 origin, whatever you do, don't try to manually drag the line until it looks like the right size. Don't do it. Instead, just type your target diameter, which is 48, directly on your keyboard and hit Enter. Boom! Your vertical line is perfectly sized. Then, to make that 50 millimeter horizontal step, just click the top of the line you just made, drag your mouse a tiny bit to the left just to show it the general direction, and type 50. For that final total length, you can literally just type in the absolute coordinate, Z100, hit Enter, and the software instantly snaps the endpoint precisely to the negative 100 millimeter mark on the Z-axis. It's like magic once you get the hang of it.
All right, let's jump into Section 3, roughing and finishing operations. Now, realistically, out in the shop, we definitely run a quick facing operation first just to clean up the front face of our raw stock. But for our main bulk material removal today, we're going to right-click over in the Toolpaths Manager and select the rough operation. You'll chain your geometry by just clicking the start of your drawing and then the end. Once you do that, the roughing parameters interface pops right up. Think of this window as the ultimate control center for your heavy cutting. But hey, before you even touch those numbers, you have to select the specific carbide insert and tool holder from the library. You want to make absolutely sure it perfectly matches the physical tool currently sitting in your machine's turret.
Inside that interface, we've got some pretty critical engineering decisions to make. First up is depth of cut, which dictates exactly how deep the tool bites into the metal on every single pass. For this explainer, we're just inputting 1 millimeter, but in the real world, you'd tweak this based on how rigid your setup is and what your cutting insert can actually handle. Next, look at stock to leave in X and stock to leave in Z. We intentionally do not cut all the way to our drawn line during a roughing pass. Nope, we want to leave a tiny little layer of material, usually around 0.2 millimeters. We do this so our finishing tool has some fresh material to slice away later, which guarantees a perfect surface finish. And finally, we set our cutting method. For standard turning, that's typically going to be a one-way directional cut.
Okay, so with the bulk of that material aggressively roughed out of the way, it's time to bring in our finish toolpath from the drop-down menu. When you're chaining your geometry for this one, you really want to utilize the partial selection and definitely check the weight box. This is a game changer. It allows you to meticulously click each individual line segment, making absolutely sure the software knows the exact continuous path that our delicate finishing tool needs to glide across.
When you open up those finishing parameters, you're naturally going to select a sharper, way more delicate tool insert. This one is meant for pure precision, not heavy material removal. And check this out. You'll notice the stock to leaf settings for both X and Z are now firmly set to 0.0. This tool is cutting right on the money, no leftovers. You can also play around with your finish step over and the number of finished passes. But honestly, usually just one pass is perfectly sufficient to sweep away that final 0.2 millimeters of material we left behind earlier. That's what gives you that gorgeous mirror-like finish on your physical part.
Which brings us to our final act, Section 4, Post-Processing and FANUC Setup. You know, we can sit here and simulate our tool paths on a screen all day long. But unless we output that data correctly, our physical CNC lathe isn't going to budge an inch. I really want you to internalize this concept straight from our source material. Numeric code generated by CAD/CAM systems is general. It needs adjustment for the target machine control environment. See, Mastercam outputs a very standard, highly detailed block of G-code, but every single machine brand out there, whether it's a Haas, a Mazak, or like in our setup today, a FANUC, has its own specific dialect and its own memory limitations. So we've got to manually refine this general code to make it perfectly palatable for our specific machine.
So for a standard FANUC controller, we actually have to make a few mandatory manual edits to the post-process text file. First off, we've got to delete the bulky header information. I'm talking about things like the file path, the date, the Mastercam version, all of that. Older CNC machines have surprisingly limited memory, so stripping out this textural fluff prevents annoying transfer errors. Second, FANUC controls are super strict. They limit program numbers to a maximum of 5 digits, no exceptions. So if Mastercam spits out a longer default program name, we have to delete it or shorten it. Third, we need to simplify our tool changes. We just strip out the unnecessary text strings and make sure the tool change command relies purely on the standard M06 numeric code. That's the specific code the machine reads seamlessly to swap the turret position.
Let's actually look at this in practice. First, take a look at the raw, generic output straight from Mastercam's post-processor. It is cluttered. You've got parenthetical comments, ridiculously long file names, and descriptive tool data that the machine's computer simply doesn't care about. And honestly, it might even choke on it. But then, look at our refined FANUC-ready code. We've completely stripped the header. We've isolated the tool calls down to just those essential M06 commands. This code is now lean, it's efficient, and it is perfectly formatted to guarantee a flawless, safe machining cycle without throwing any controller alarms. And there you have it, students. We literally just went from a totally blank screen to a fully optimized FANUC G-code program. We navigated the workspace, drafted some precise geometry, calculated an aggressive roughing pass and a delicate finishing pass, and finally, optimized the actual machine language. So my final provocative question to you is this. How will you apply these virtual Mastercam programming strategies to your own real-world physical machining challenges? Seriously, think about how the digital choices you make today will directly affect the physical metal you cut tomorrow. Keep practicing those wireframes, always double-check your tool clearances, and I'll see you right back here in our next explainer. Happy programming!